Now that we've visualized the behavior, let's show how it's implemented. This is going to look ridiculously similar to what we did before, but it'll work so much faster. So here's processStream. As you'll see, there's a minuscule change here. The difference here is instead of saying stream, we say ParallelStream. And what that'll do by saying ParallelStream, if you recall, what happens there is that ends up calling the stream_support.stream method with the split iterator, which in this case will be make an array list, and it also has the parameter true to the stream_support.stream method, and that says make a parallel stream. So go ahead and use that split iterator's try split method to split things up into chunks that can then be fed to the underlying fork join pool. So that's what it's going to do. It's going to slice it up into chunks. And what's going to happen is these chunks we end up with, and we'll end up really with one chunk for each input string. That's the way it works for an input. That's an array list. And each of those chunks will then be thrown into the common fork join pool. So all those different things will run in parallel, but of course each chunk is processed sequentially in terms of itself, but all of the chunks will run in parallel in that pool. So each input string is processed in parallel using the common fork join pool. Then, as you can see here, we're going to call map. So this is where it's actually running. This is actually where it's doing the real work. It's going to call processInput in each of those chunks. And that will then search for the phrases in that given string. And then we're going to collect everything into a list, which, as always, triggers intermediate operation processing. And here's the key thing. It'll merge the partial results into a single list of search results. And as I mentioned before, collectors toList, which is this method here, returns a non-concurrent collector that will obey the encounter order. So it'll end up with an array list of results in the encounter order, whatever the order the plays of Shakespeare were given will be the same order that they come back here. Let's take a look at processInput, pretty much the same idea. So we start out by using ParallelStream to take the phrases we want to find, and under the hood, that will call the stream_support.stream method on m phrases to find, which will take that thing called the split iterator, make an array list, and then feed those into the common fork join pool. So there'll be the common fork join pool. Notice that we call the search for phrase method with the false flag set here. This is important because we'll talk about this later when we talk about the search with split iterator example where we're going to pass in a true value here. So for right now, we're only getting parallelism in 2 dimensions. Parallelism in terms of the number of input strings and parallelism in terms of the number of phrases to look for in each input string. Those are the 2 things that are running in parallel. So if you take a look under the hood, in this case, we take the phrases for a given input string, and then we take those phrases and we stick them into the same common fork join pool that everything else gets processed in. So each phrase and each input will be processed in parallel in the common fork join pool. And just keep this in the back of your mind. We'll talk about this more later, but as a general rule of thumb, especially if you have a lot of cores and you have a lot of input and you have a lot of processing, the more you can break your input up into smaller chunks to get a lot of things to run in parallel and then throw all of those things into the one and only common fork join pool, typically the better your performance will scale. And why is that? Because you've got more things to do with the available cores. And this, of course, is the whole beauty of data parallelism, is that as you scale up the number of independent processing elements, you can leverage the new world Moore's law where we have more cores. Look. Oh, great question. So the question here is, at some point, let's say, just for sake of argument, we've got 4 threads. Let's say we have 4 cores, right? And so if you have 4 cores, your common fork join pool will have typically the number of cores minus 1 threads, And the reason for that is that the thread that is calling the stream will also be included. So to make it life easier, let's just imagine we have as many threads as there are cores that are doing work in parallel. So as you can imagine here, if we have lots of works of Shakespeare, there's some 36 to 37 independent works of Shakespeare, and there could be as many phrases as we want to look up. We could have hundreds or thousands of phrases. We'll very quickly end up with more elements, more things to run in parallel than we have computations that could run in parallel. For compute-bound jobs like this one, because keep in mind, searching for something in a string is fundamentally a compute-bound job. You're not having to wait for I/O. You're just going to go ahead and process the in-memory data looking for a match, right? For those kinds of environments, all that'll happen here is there'll just be queues of work pending in the pool of worker threads, because internally, we'll talk more about this later, but internally, each thread in the worker pool has its own internal queue, which is actually a deck, a double-ended queue, but think of it as a queue. So as more work comes along and we have cores/threads to do it, those queues will just grow longer. And there's a really cool thing called work stealing under the hood that will make sure that the queues are kind of accessed and processed in a balanced way. So for compute-bound jobs like this one, the fact that we have more work than threads, we just queue things up. It gets a lot more interesting when we talk about I/O-bound jobs. So searching strings for patterns is not I/O-bound. But downloading images, like you guys are doing for your programming assignments, or as we'll talk about when we do a variant of this later, where we have the image stream gang program, those are I/O-bound tasks. And I/O-bound tasks actually benefit from being able to have more threads than cores. And that's because when an I/O-bound job is blocked on I/O, because it's I/O-bound after all, whenever it's blocked waiting to read something in or write something out, if there's another thread that can make progress while one thread is blocked, we really want that thread to get a chance to preempt the thread that's blocked and get a chance for it to run. So we'll come up later and we'll talk about a really cool formula that's used to figure out what the right number of threads should be in a pool that has I/O-bound work in it. And then we'll also see some really cool features that you can use that are part of the common fork join pool to automatically expand and contract the number of threads in the common pool based on what's blocking and what's not blocking. So that's an attempt at trying to be adaptive, to dynamically modify the behavior of the thread pool, of the common fork join pool. So we'll talk about that when we get a little bit more into the details. Well, especially when we get into the discussion of the common fork join pool, I will give you all the nitty-gritty of how it works under the hood. And it's really, really, really cool. But right now, for this simple example, if there's more work to do than there are cores/threads to do it, the number of threads does not increase. The queues simply get longer. And that's, everyday life is full of examples like this, right? If you go to the supermarket, you go to Publix or Kroger or wherever you shop for food, where there are typically, 12 aisles. At any given point in time, you'll have, N cashiers working on those aisles. And if they don't have sort of, all the aisles full, if more people show up, you just get longer lines, right? And occasionally you'll have a situation where it's like, all sales associates who are not helping customers come to the front and, check people out. That's what you do. You adapt the number of threads running in the cashier queues, processing queues of cached customers who want to get processing done. Yeah, that's a great question. As before, collect triggers intermediate operation processing. We merge the results together into a single list. No big surprise there. And we return the list of search results. So a lot of this stuff looks the same. The structure of the code is almost identical with ParallelStream and stream replaced. But the actual behavior under the hood is wildly different when we do parallel streams. And you have to be aware of that. Otherwise, you can get situations where you don't actually get a win by using parallel streams at all. And we'll talk about that too. OK, so that wraps up the implementation